So, we will start discussing problems on gaseous chapters. So, we will start with a very simple problem. Problem number 1, it says calculate the volume occupied by 5 moles of an ideal gas at 5.5 times 10 to the 5 Newton per meter square pressure and 298 K temperature. The value of R is given. It is given in Newton meter or in joule unit. So, the solution is extremely straightforward. Okay, so, we know for ideal gas PV is nRT. Here N is 5 and value of R is 8.314 in Newton meter unit, and pressure P is 5.5 times 10 to the 5 Newton meter to the minus 2. So, we need to calculate the volume. So, volume is nRT by P. So, if you substitute all these values of N, R, T and P, and temperature is also given, T is 298 K. So, we get N is 5, R is 8.314 and temperature is 298 by P, P is 5.5 times 10 to the 5. So, it gives 22.52 times 10 to the minus 3 meter cube. So, this was extremely easy problem. So, the next problem is determine the total pressure of a gas mixture when 1.5 liter hydrogen and 0.5 liter oxygen each at 0.5 bar are placed together in a 2 liter container at 27 degrees Celsius. Okay, so, the information given are V1, the solution is, so V1 is 1.5 liter, P1 is 0.5 atmosphere or 0.5 bar, they are very close, and V2 is 0.5 liter and P2 is also 0.5 atmosphere. Okay. So, we will proceed it. So, according to Boyle's law, we know, okay. So, P1 V1, or we can write for oxygen gas, P1 is 0.5 atmosphere, we write for oxygen gas PO2, okay, 0.5 atmosphere, volume of oxygen given. So, volume of oxygen VO2 is 0.5 liter. Okay. So, now final volume V is 2 liter here. So, the partial pressure when they put together, so partial pressure of oxygen is 0.5 times 0.5 by 2, this is in atmosphere or bar. Okay, so, we can write this is 0.125 atmosphere or we can write 0.125 bar, they are very close, and partial pressure of hydrogen is 1.5 times 0.5 by 2. So, it will give you 0.375 bar. So, total pressure is 0.125 bar plus 0.375 bar. So, it will give you 0.5 bar. So, the first part here we write this one is volume of hydrogen and initial pressure of hydrogen. So, we just modify this one. So, here volume of oxygen and then this is initial pressure, if we say initial pressure again, initial pressure of oxygen. Okay, then we can do it very easily. Okay. So, this is problem number 2. Next we go to problem number 3. It says blood circulation in the human body delivers oxygen and eliminates carbon dioxide. On average 100 ml of blood contains 0.4 gram of oxygen and 0.1 gram of carbon dioxide. Determine the volumes of oxygen and carbon dioxide at 1 atmosphere and a body temperature of 37 degrees Celsius, given that the total blood volume in the body is 9 liter. And you have to use the value of R gas constant is 0.0821 liter atmosphere per Kelvin per mole. So, we start with volume of blood first. Okay, so, solution is, so volume of blood is 9 times 1000 because this gives you 9000 ml. And weight of oxygen in the blood is 0.04 times 9000 by 100. So, we get 3.6 gram. Next we calculate weight of carbon dioxide in the blood. It will be 0.1 times 9000 by 100. So, it will give you 9 gram. So, we know PV equals to N at T. So, for oxygen, number of moles of oxygen, if we say this one is NO2, is 3.6 by 32. This is mole, right? Because we got the weight of oxygen is 3.6 gram and the molecular weight of or molar mass of oxygen is 32. And so, V of oxygen will be your 3.6, number N, R is 0.0821, T is 310 because 37 degrees Celsius, T is 37 degrees Celsius means 310 K, 310 by 1. So, you get is 2.86 liter. Okay. And for similarly, if we carry out this for carbon dioxide, for CO2, number of moles of CO2 is 9 gram CO2 we have and 44 is the molar mass of carbon dioxide. So, volume of CO2 is 9 times 0.0821 times 310 by 44. So, if we carry out this one, we get 5.2 liter. So, this was problem number 3. Next, we go to problem number 4. Calculate the total and average kinetic energy of 48 gram of methane molecules at 27 degrees Celsius. Value of R is given. Okay, so average kinetic energy per molecule average kinetic energy per molecule. We say, so E is the total number of moles of what is called this methane or molecule. So, average kinetic energy, if we say, so average kinetic energy, we write epsilon kinetic energy is 3 by 2 kVT, because we know kinetic energy E is 3 by 2 RT for 1 mole. Okay. So, R is n number of moles, suppose. Okay. So, if we write n RT, so R is Na times Kb, Avogadro number, times Kb, Boltzmann constant, times T. So, if we divide E, and n times Na is your total number of molecules, and number of moles times Avogadro number gives you total number of molecules. So, if you divide E by n times Na, that will give you average kinetic energy per molecule. That is what we are getting here, and this gives you kBT, 3 by 2 kBT. So, that is how the average kinetic energy per molecule is coming here. So, average kinetic energy per molecule is this. So, now you substitute the value. So, if we multiply this Kb by Avogadro number, okay, so we get kinetic energy of 1 mole. Okay. So, average kinetic of a single molecule is 3 by 2, Kb is R by Na, right, we just discussed, Kb is R by Na. So, R is 8.314 in joule unit, by Na is Avogadro number, so 6.022 times 10 to the 23, and the temperature is given is 27 degrees Celsius, means 300 Kelvin. Okay, and then if we do it, we get 6.21 times 10 to the minus 21 joule. So, this is the average kinetic energy of a single molecule. So, how many methane molecules are there? So, 48 gram methane molecules, right. So, 48 grams of methane molecules means get number of moles of methane molecules NCH4 is 48, and the molar mass of methane is 16. So, we get 3. Okay, so, 3 is the number of moles of methane. So, number of methane molecules in 48 gram CH4 is 3 times Avogadro number Na. So, the total kinetic energy is 3 times Na times 6.21 times 10 to the minus 21 joule. So, 3 value of Avogadro number is 6.022 times 10 to the 23 times 6.21 times 10 to the minus 21. So, if you carry out, so you get 11.223 kilojoule per mole. So, this is the value of average kinetic energy is this one, and the total kinetic energy is this one. Next, we move to problem number 5. It says, given that the average velocity of a gas at temperature T1 equals the most probable velocity at temperature T2, and both velocities are 5 times 10 to the 4 with the molar mass of 44. Find the temperatures T1 and T2. So, we know the expression for average velocity. Okay. So, average velocity if we call C average is root over 8 RT by pi m, and most probable velocity, the expression for most probable velocity, if we call this is CMP, is root over 2 RT by m. M is the molar mass of the molecule. Now, what the problem says? Problem says, given that the average velocity of a gas at temperature T1 equals the most probable velocity at temperature T2. So, 8 RT root over square root of 8 at T1 by pi m is root over 2R T2 by m. The value is given 5 times 10 to the 4. Now, molar mass is given. So, root over 8 at T1 by pi, and the value of m is 44. Remember, this 44 is given in gram. So, we need to convert this one by into kg. So, we have to multiply this by 10 to the minus 3. So, this gives you 5 times 10 to the 4. So, if we now square both sides, then we get 8R T1 by pi times 44 times 10 to the minus 3 gives 5 times 10 to the 4. So, the value of T1 is 5 times 10 to the 4 times 3.14 times 44 times 10 to the minus 3 by 8 times R. So, value of R here we will be using in joule unit. So, velocity is given in centimeter per second. So, we need to convert into meter. So, we have to multiply this factor by 10 to the minus 2, 10 to the minus 2, and then its square. Okay, so, value of T1, so value of T1 is 25 times 10 to the 4 into 3.14 into 44 into 10 to the minus 3 by 8 times 8.314 times 8.314. So, if we do it, you get the value of temperature T1 is 519 Kelvin. If we carry out similar exercise for T2, so we get T2 is 5 times 10 to the 2 square by 2R, so 2 times 8.314, and then we need to multiply it by 44. So, if we carry out this one, we get 661.5 Kelvin. So, these are the values of T1 and T2. The RMS velocity, root mean square velocity of hydrogen is root over 7 times the RMS velocity of nitrogen. If T is the temperature of the gas, then which one is correct? So, what is the expression for RMS? VRMS or CRMS? So, the RMS velocity, if we say this is CRMS, is root over 3 at T by m. Now, the RMS velocity of hydrogen is root over 7 times the RMS velocity of nitrogen. So, CRMS of hydrogen is root over 7 times CRMS of nitrogen. So, if we say that, so what is the CRMS of hydrogen? Root over 3 R T of hydrogen by m of hydrogen. So, we get root over 3 R T of hydrogen by m of hydrogen is 2 times 10 to the minus 3. Similarly, CRMS of nitrogen is root over 3 at T N2 by, for nitrogen the molar mass is 28. So, 28 times 10 to the minus 3. Now, it says, okay, so CRMS of hydrogen is root over 7 times the RMS of velocity of nitrogen. Okay. So, we write root over 3 R T hydrogen by 2 times 10 to the minus 3 is root over 7 times root over 3 RT into by 28 times 10 to the minus 3. If we square root both sides, so we get T of hydrogen by 2 times 10 to the minus 3 times 3R gives you 7 times 3 RTN2 by 28 times 10 to the minus 3. Now this 3R gets cancelled, so we get 10 to the minus 3, 10 to the minus 3 gets cancelled, you get this one is 4 and this gives you 2. So we get TH2 is 2 times TN2. So option B is correct. So B is correct. So this was problem number 6. Next we move to problem number 7. It says 1 mole of carbon dioxide occupies 2.5 liters at 27 degrees Celsius. Determine the pressure exerted by carbon dioxide using the ideal gas law and the van der Waals gas equation. Given A, value of A and value of B are given. So number of moles N is 1, volume is 2.5 liter, temperature is 27 degrees Celsius. So 27 degrees Celsius is 300 Kelvin. So for considering ideal gas equation of state, so P ideal is nRT by V. So you get P ideal is N is 1, R is, so since we will be using liter for V, so we need to use R, value of R is liter atmosphere, so this is 0.082, it's in liter atmosphere mole to the minus 1 and then K to the minus 1, and then T is 300 K and this is 1 mole by V is 2.5 liter. So if we carry out this one, we get P ideal is 9.9 atmosphere. Now van der Waals gas equation of state is P plus n square A by V square times V minus NB is nRT. So if we simplify further this one, we get V is nRT by V minus NB minus n square A by V square. So if we substitute everything, we get n is 1 here, R is 0.082, T is 300 by value of V is 2.5 in liter, and value of B is also given liter per mole. So V is 2.5 minus N times B, N is 1, B is 0.02. So this is V minus NB and then minus N square. So 1 square times A is 1.8 by V square, V is again 2.5 square. So if we simplify this one, we get P is 9.75 bar or atmosphere. Okay, so we can write atmosphere also. So this is problem number 7. So next we move to problem number 8. It says calculate the compressibility factor Z of 1 mole sulfur dioxide if the volume occupied is 500 ml at 27 degrees Celsius and 4 times 10 to the 6 Pascal pressure. So pressure is given in SI unit. So we need to convert volume also in SI unit, or we can convert pressure into atmosphere. So we know 1 into 10 to the 5 Pascal is 1 atmosphere roughly. So 4 into 10 to the 6 Pascal gives you 4 into 10 to the 6 by 1 times 10 to the 5. So it gives you 40 atmosphere. This is the pressure. Okay, so volume is given in ml, so 500 ml, so we convert into liter. So liter is 0.5 liter. So PV is done. Now T is 27 degrees Celsius. So Z is PV by RT, right? So value of P is, we got 40, V is 0.5, R, so we are considering liter atmosphere here, so we need to consider liter atmosphere here also. So 0.082 and temperature is given 300. So 27 degrees Celsius means 300 Kelvin. So this is 300 Kelvin. So if we do it, we get Z is 0.81, okay, or 801. Okay, this was problem number 8. Next we move to problem number 9. It says the critical constant for water are 374 degrees Celsius, 217.7 bar and 0.0566 liter per mole. So TC is given, PC is given, VC is given. Calculate A and B constant. So data given are TC is 374 degrees Celsius. PC is given 217.7 bar, means roughly 217.7 atmosphere we can say, and VC is given 0.0566 liter mole to the minus 1. So we know, so PC is A by 27 B square, that we know. TC also we know, 8A by 27 RB, and VC we know 3B. So B we can calculate very easily. So B is VC by 3 and the value of BC is 0.0566 by 3. So we get 0.0189 liter mole inverse. This is the value of B. Now we need to calculate value of A. Now PC is A by 27 B square. So A is 27 B square times PC. So you get value of A is 217.7 times 27 times B square is 0.0189 square. So we get value of A is 2.09 atmosphere liter square mole to the minus 2. This was problem number 9. Next we move to problem number 10. It says a gas can be liquefied at temperature T and pressure P provided option A is T equals to Tc and P is less than Pc. Option B is T less than Tc and P greater than Pc. Option C is T greater than Tc and P greater than Pc. And option D is T greater than Tc and P less than Pc. What is the expression? Gas can be liquefied. We know gas can be liquefied if the temperature is lower than critical temperature Tc and pressure is greater than critical pressure Pc. So, gas can be liquefied when T is less than Tc and P is greater than Pc. So, option B is the correct option.